If you love cats, or you're just curious, you're going to be surprised by what I'm about to show you. Imagine being dropped from a height of about 5 feet. You'd hit the ground in exactly the same position you started in. A cat, on the other hand, can move while it's falling and land on all four paws without touching anything on the way down. Physics has a rule that says this shouldn't work. So how does it? The rule is called the conservation of angular momentum. Put simply, an object only starts spinning if something external makes it spin. While falling through the air, there is no such external force. Gravity pulls the entire body through its center of mass and doesn't produce any rotation. A cat leaves someone's hand with absolutely no spin, and half a second later, its back is facing upward. The rotation seems to have appeared out of nowhere. And in physics, out of nowhere is not a phrase you can casually throw around. This contradiction and what looked like the cat's magical ability even bothered serious scientists. In 1894, when the first high-speed photographs of a falling cat were presented to the French Academy of Sciences, part of the audience accused the experiment of being fraudulent. There was also a study conducted in New York in which cats that fell from higher floors actually suffered fewer serious injuries than cats that fell from lower floors. That has an explanation too. You're probably thinking, oh, this one's easy. Nope. The answer isn't the tail. That's what most people guess, and it's the very first thing the evidence rules out. Now, before we look at the cat itself, it's worth looking at the rule it seems to break. Angular momentum is the amount of rotational motion an object has. It depends on three things: its mass, how fast it's spinning, and how that mass is distributed relative to the axis of rotation. The classic example is a figure skater. She spins with her arms extended, then pulls them in close to her body and suddenly spins much faster. Nobody pushed her. She simply brought her mass closer to the axis. Since angular momentum has to stay the same, her rotational speed increases to compensate. The second part of the rule is the one that matters here. Without an external force producing torque, the total angular momentum doesn't change. If it starts at 0, it stays at 0. An object in free fall is in exactly that situation. But there's one detail that usually flies under the radar. Having a total angular momentum of 0 doesn't prevent the body from ending up facing a different direction. Now think about someone sitting in a swivel chair. If someone gives them a push, they spin. But imagine a different situation. That person crosses their arms, bends their legs, twists their torso, and then undoes those movements in a different order. Throughout the whole process, they can end up slightly turned in a different direction, even though nobody ever pushed them from the outside. They never created continuous rotation. They simply rearranged their own body in a very specific way. The secret lies precisely in that sequence of movements. Angular momentum describes an object's state of rotation. Orientation describes which direction it's facing. Those are two different things. A rock can't do this because it's rigid. A cat isn't. A cat can, because it bends its spine, moves its legs, and redistributes the mass of its own body. The interesting part is that the first time anyone was able to watch this fall in slow motion, it sparked an academic controversy. Étienne Jules Marey was a French physiologist obsessed with breaking movement down into its individual components. He developed chronophotography, a technique that captured dozens of images per second on the same photographic plate, and spent his life pointing that camera at people running, birds flying, and water flowing. In 1894, he pointed it at a cat released upside down. The sequence of images showed, frame by frame, what no one had ever been able to see with the naked eye. When the cat was released, observers saw that the head rotated first. The front half of the body followed. The back half came afterward. And the entire body lined up with the ground before it ever touched the ground. The reaction at the French Academy of Sciences was one of skepticism. Some of those present argued that the cat must have been receiving a push from the hand that released it, a kind of initial twist. If that were true, the problem would be solved. There would be an external force, there would be torque, and the mystery would disappear. The first frames showed no such thing. Mary's own interpretation was that the cat used the inertia of its own body, rotating one part against the other. Describing what happens, however, is different from explaining how it happens. The model accepted today didn't stand on solid ground until the following century. The entire model can be understood through two movements. And what's striking about the second one is that it's the exact opposite of the first. The cat's great trick can be summed up in just 2 words: bend and twist. The cat's spine bends sideways around the waist. In practice, this divides the body into 2 segments that can rotate independently. The front half, made up of the head, chest, and front legs, and the rear half, consisting of the hips and hind legs. The first movement, the front legs are pulled in tight against the body, close to the axis of rotation. This reduces that segment's resistance to spinning. At the same time, the hind legs extend outward, farther from the axis, increasing the rear half's resistance to rotation. Now both halves rotate in opposite directions, exactly as the law requires, so that the total remains 0. But because the front half has very little resistance to rotation, while the rear half has much more, the front rotates a lot, and the back rotates only a little. The result of the first movement, the front half gains a large change in orientation. The rear half changes very little. The second movement reverses everything. The front legs extend outward, and the hind legs tuck in. Now it's the rear half that rotates a lot, while the front barely rotates at all. The rear catches up with the front. Repeat that cycle once or twice, and the entire body ends up turned around. At every instant, the sum of the 2 rotations remains 0. The law is respected from beginning to end. It's the same principle as the figure skater's arms. The difference is that the cat isn't using it to spin faster. It's using it to make one half of its body win the rotational tug-of-war against the other. Try to picture the whole process in your mind. They're remarkably clever movements that produce a perfect result. But as impressive as nature's design is, we also have to recognize that something has to tell the body it's upside down. Inside the inner ear is a group of structures known as the vestibular system. Within it are tiny calcium carbonate crystals called otoliths, which rest on sensory cells. Gravity pulls on these crystals, and the way they tilt tells the brain which direction is down. A fall changes that signal abruptly. In high-speed recordings, the sequence is always the same. The head aligns first, the chest follows. The hips complete the sequence. It's a chain reaction that travels from front to back. 2 anatomical features make this possible. A cat's spine is extremely flexible, and its clavicle is small and not rigidly attached to the rest of the skeleton, giving the shoulders a great deal of freedom of movement. Without that extra flexibility, the bend and twist maneuver wouldn't be possible. This is where 2 clarifications come in that clear up almost every popular misconception about the subject. The first is the tail. It contributes very little. Breeds with short tails or no tails at all can still right themselves in midair. The tail helps with fine adjustments. It isn't the source of the rotation. The second is that this ability isn't there from birth. The righting reflex begins to appear at around 3 to 4 weeks of age and reaches its fully developed form at about 6 to 7 weeks. And there's a limit. The sequence takes time, a fraction of a second, and in a fall, time means height. Below roughly 1 foot, there simply isn't enough time to complete the rotation. Which brings us to the uncomfortable part. Turning in time is one problem. Walking away unharmed is another. This is where the New York data I mentioned earlier comes in. Landing on its feet doesn't protect a cat from getting injured. The rotation solves the orientation problem. That's all. The energy of the fall remains exactly the same. The legs act like shock absorbers. The joints flex upon impact, slowing the body over a greater distance, which reduces the peak force. Even so, falls from significant heights routinely result in fractures of the jaw, chest, and limbs, injuries that veterinarians treat on a regular basis. Cats always land on their feet describes a tendency, not a guarantee. Now, back to that New York study. In 1987, 2 veterinarians published an analysis of 132 cats treated after falling from buildings, with an average fall height of about 5.5 stories. The expectation was straightforward. The higher the fall, the more severe the injuries. What they found was the opposite. Cats that fell from above the 7th floor suffered, on average, fewer serious injuries than those that fell from the 2nd through the 6th floors. The proposed explanation involves terminal velocity. A falling object accelerates until air resistance equals its weight. From that point on, its speed stops increasing. For a cat, estimates place terminal velocity at around 60 miles per hour, reached after roughly a 5-story fall. While accelerating, the body remains tense and compact. Once acceleration stops, the sensation of falling changes, and the muscles tend to relax while the legs spread outward horizontally. A larger surface area creates more air resistance, slightly reducing speed and distributing the impact over a broader area instead of concentrating it on the paws. One important disclaimer about those findings. The study only included cats that made it to the veterinary clinic. Animals that tragically died at the scene were not part of the data. The researchers themselves acknowledge this selection bias in the discussion section of the paper, which means the results are suggestive rather than conclusive. So a cat falling in the best possible way to avoid injury isn't an exception to the laws of physics. It's a demonstration of something about physics that took a century to be properly understood. A fall from just over 3 feet lasts less than half a second. During that brief interval, with nothing to push against, the cat reorganizes the shape of its own body and reaches the ground without violating a single law of physics. If you enjoyed learning about this phenomenon, and if you love cats, go ahead and share this video with someone else who'd love to know how this works too.